This video covers pressure, which is our first topic under fluids. Now this video has a lot of information, but I only want you to write down the colored pieces. First of all, when we mention fluids, we're talking about both liquids and gases. Both of these are states of matter that flow. So don't forget gases are also included in this. Now you've seen density before, usually in your chemistry classes. Density is going to be represented by a Greek letter rho. Sometimes we might have p's and rho's in the same equation, so it's going to be important that you be able to distinguish between the two. Mass is going to be represented by an m, still units of kilograms. Volume is going to have units of meters cubed. And density will have kilograms over meters cubed as its unit. Now, in chemistry, you use grams per milliliter, so it's going to be important that you make that distinction. Now, also a really important number that you're going to need to memorize is the density of fresh water, which is 1,000 kilograms per meters cubed. Pressure is the total force of many atoms delivered to an area. So pressure, represented by a capital P, is equal to force divided by area. This is measured in newtons per meters squared, also known as a Pascal, represented by capital P, lowercase a. Now this equation tells us a relationship between force and area. So if you wanted to decrease your pressure, you would have to do one of two things. You would have to either decrease your force or increase your area. So we saw an example of a person sitting on a bed of nails versus laying down on one. Now, we said that this doesn't really hurt, and the reason for that is our decrease in pressure. When we lay down on that bed of nails, what you're doing is you're increasing the area, therefore decreasing pressure. So there's going to be a couple of other numbers you're going to need to know. Now, pressures are often given in atmospheres and will need to be converted into pascals. So 1 atmosphere is equal to 101,325 pascals. But on the AP exam, it's allowed to be rounded off to 100,000. So 1 atmosphere is going to be equal to 1 times 10 to the 5th pascals. And we'll see a conversion chart a little bit later. So again, you don't need to write all of this down. This conversion chart is going to be information you're going to need to know. A lot of information is given in grams or centimeters or milliliters, and you're going to need to convert that to kilograms, meters, or meters cubed, depending on the unit. So, make sure that you include these in your notes, and take extra note of going from centimeters squared to meters squared, or centimeters cubed to meters cubed. Because you have something that's being squared or cubed, you're going to also need to square or cube the actual conversion. So just a quick example of how we can use this chart. Let's say we have 1 milliliter, and we want to convert to meters cubed. That's simply 1 times 10 to the negative 6, which is our conversion, meters cubed. So just a couple of quick examples. It says determine the density of a 250 gram mass occupying a volume of 0.5 liters. So if we want to solve for density, rho, it's equal to mass over volume. So remember that mass is 250 grams. So times 10 to the negative 3 to make it into kilograms. And then we have 0.5 liters. So we multiply it by 10 to the negative 3 to convert to meters cubed. So our density is 500 kilograms per meters cubed. The second example, determine the density of a 50 gram mass occupying a volume of 2.0 centimeters cubed. Again, we have that 50 grams that's being converted to kilograms, so times 10 to the negative 3. And we have that 2 centimeters cubed that's being converted into meters cubed. So that's times 10 to the negative 2 is our conversion to meters, and then cubed is our conversion to meters cubed. So we get 25,000 kilograms per meters cubed. So the next couple of slides build this idea of pressure equals force over area and how that comes to another equation we use a lot. So I'm going to tell you the important parts you're going to need to write, so just listen until we get there. So when you go scuba diving, the weight of the water above you creates a pressure on you. The water above your head forms a column that extends from your head all the way to the surface. The column has an area A that matches the area of your head and shoulders. It also has a height h that represents the depth that you are diving at. The area and height together describe the volume of the column. As you go deeper, the area of the column does not change, but the height does increase, which increases the weight and pressure. So, if height is so critical, we need to make sure that this is worked into our equation. So what we can do is multiply the area by height, but also multiply our force of gravity by height, so that it doesn't change our equation, because technically we're being multiplied by 1. So if the area is equal to height, and height describes the volume of the column, and we know that mass over volume gives us density, then this equation can be rewritten as pressure is equal to rho times gravity times height. So it's important that you get this equation down in your notes. So the really important part is that this equation only solves for the pressure of the fluid you are examining. It is called a gauge pressure, as this would give you the reading of a pressure gauge submerged in the fluid. However, this is not the entire pressure on you when you are at the bottom of the lake. There is another fluid above the water, and this fluid's pressure is not recorded by the gauge. Now remember that the fluid above the water is the air, and gases are fluids. There is a column of air extending from the lake to space. The pressure of the air on Earth at sea level is known as P naught, which is 1 atmosphere, or 1 times 10 to the 5th pascals. So if we wanted to calculate the absolute or total pressure, then we would have to sum the air pressure and any other fluids, such as the water, which is this equation down here. So again, the pressure experienced by the person down in the lake is both the air pressure plus the pressure of the water above the person. So whether you work with gauge pressure or absolute pressure, the key variable is height of the fluid column. The greater the height, the greater the pressure. Rate the pressure at the points below from highest to lowest. So again, the most important part is the height. So the pressure increases as the height above it increases. So E has the greatest pressure exerted on it. B, C, and F all have the same pressure on it because they all have the same height above it on it. And A and D also both experience the same pressure. Horizontal motion does not change the pressure, only depth does. Again, 2 more quick examples. A scuba diver is 15 meters below the ocean surface. Now, here, it's very important that you see that this is the ocean surface, and we know that oceans have salt water rather than fresh water, so the number that we had before isn't going to quite work. So in order to figure out our gauge pressure, we're going to need to know the density of salt water. This is not information that you're going to need to memorize. Usually if it's asked of you, you'll be given these values. So the density of seawater is 1.03 times 10 to the third. Gravity is 9.8, and our height will be 15 meters. So if you multiply all these values out, you get 1.514 times 10 to the 5th pascals. Again, this is asking for just gauge pressure. If you were asking for absolute pressure, you would have to add our atmospheric pressure, which is 1 times 10 to the 5th, to our gauge pressure, which was 1.514 times 10 to the 5th, to give us a value of 2.514 times 10 to the 5th pascals. So do include this blue piece in your notes. A gas is trapped in the bulb on the left by water, in gray. The unknown gas has enough pressure to cause the water to form a column that is H is equal to 40 centimeters tall at point B. So again, this piece that is not colored in, all of this is a gas that's trapped in by this. It might be confusing that I used blue. This gray piece is what's water. Now, if we analyze both point A and point B, we notice that they're both located at the same height. So, the pressure at point A is also the same as the pressure at point B. Since that's true, then we can use that the pressure at point A is equal to the pressure at point B to help us solve for the pressure of the trapped gas. So the important part we're going to need to remember here is that the fluid above each point causes the pressure on that point. So above point A is the trapped gas. Above point B is both water and atmospheric pressure. That means that the pressure of the gas is equal to atmospheric pressure plus the pressure of the water. So if we substitute in all our values, our atmospheric pressure is 1 times 10 to the 5th pascals. Our density of water, we can assume it's fresh water here, is 1,000 kilograms per meters cubed. Gravity is 9.8 or 10. And height in this case is 40 centimeters or 0.4 meters. So this information gives us the pressure of the gas at point A, which is 1.04 times 10 to the 5th pascals. Another device common in this unit is a barometer, and these are used to determine air pressure. Now again, if we examine point A and point B, we can see that the pressure will be the same at both points. Now, this problem says a column of mercury is trapped inside of a tube, so the gray piece is mercury. The space above the fluid column is a vacuum. That means that we don't have air here, so we don't have air pressure. The bottom of the tube is immersed in a dish open to the air. That means that this is air, and we do have atmospheric pressure at that point. The purpose is to find the atmospheric pressure at point A. The fluid is mercury, and the column is H is equal to 78 centimeters tall. So again, we know that our pressure at A is going to be equal to our pressure at B. So if this is true, we can say that our atmospheric pressure is going to be equal to our rho G times H. Again, we don't have atmospheric pressure here because this is not air. It told us in our problem that it was a vacuum, and a vacuum is a space with no air. So we can see that our air pressure is going to be some number other than that 1 times 10 to the 5th that we talked about earlier. Here, the density of mercury is 13.6 times 10 to the 3rd. So we'll use that number here. Gravity, again, 9.8 or 10. and our height is 0.78 meters. So we get a number that's 1.04 times 10 to the 5th pascals. Again, we can see this number is slightly bigger than our normal atmospheric pressure. And that's okay, because barometers are used to find the exact atmospheric pressure at a certain point. This also helps in predicting the weather. This last example says, a pump in a freshwater reservoir pumps water uphill into a holding tank. The height between the surface of the tank and the surface of the reservoir is 10 meters. Determine the pressure of the pump to keep water flowing into the tank at a constant velocity. If the pump is turned off, the water will go no higher than this point. So the pressure of the pump pushing up the hill must equal the pressure of the water above this point. Atmospheric pressure is pushing on the reservoir and the tank. So again, if we look at this point, we can see that it's going to experience atmospheric pressure and a pressure by the pump. On the other side, it will also experience atmospheric pressure, but it will also experience a pressure exerted by the water. So, we see that our atmospheric pressures are actually going to cancel out. And so our pressure of the pump needs to be our rho times gravity times height. Or, assuming it's fresh water, 1,000 times 9.8 times the height, which was 10 meters in this case. That means that our pump has to produce a pressure of 98,000 pascals in order to keep water moving.